second workshop. My first talk here was about Painlevé equations, namely about how one can prove explicit representations of general solutions of Painlevé equations in terms of, say, Fredholm determinants or series. So this is an example of a Painlevé equation, the so-called Painlevé-3 equation of type D8, or more familiar radial Saint-Gordon equation. So here we are interested in finding the general solution depending on two arbitrary integration constants, so a second order nonlinear ODE. In this talk, I will try to discuss a relation between Painlevé functions, that is, solutions of equations of this type, to two other types of special functions. So one of them will be accessory parameters in the differential equations of Heun type. Like in Painlevé case, you have a whole hierarchy of these Heun equations and their confluent versions, and the linear counterpart of this Painlevé-3 D8 is this classical linear Mathieu equation, that is the Schrödinger equation with just cosine potential. And here what you want to know is the energy, which is the accessory parameter, as a function of the coupling constant R, so it's the same R as here, and quasi-momentum, which is basically the monodromy of psi. And I will show that these two types of special functions, they are actually related to some functions which appear in Liouville conformal field theory. So this is a particular quantum field theory in 2 dimensions, and the mathematical name for it is representation theory of Virasoro algebra. So the algebra is here. It has an infinite number of generators, Lm, which satisfy these commutation relations. So here you have a parameter in the commutation relations, which is called the central charge. So this is just arbitrary complex number. And it turns out that when C is equal to 1, then the corresponding conformal blocks are directly related to the general solution of this equation here. On the other hand, when you consider the so-called classical limit of these conformal blocks, so this corresponds to sending the central charge to infinity in some way, then this procedure yields the Mathieu accessory parameter. Okay. Yes, so it's a classical but perhaps not so well-known fact that well, Painlevé-3 functions and Mathieu accessory parameter are related by basically when you study the local behavior of the function q, which is the exponential of I phi, when you study the behavior of q in the neighborhood of its movable poles in the complex plane, then it is described precisely by the accessory parameter here. What I am going to explain is that so it will be a different kind of relation between these two functions, which comes from here. So in the theory of conformal blocks, one has some relations which relate conformal blocks with two different central charges. And under appropriate specialization of parameters, the central charges can be made 1 and infinity, and this gives like a very concrete identity between involving phi and E. Yeah. No, it's basically this. So the finite part of this Q function near a movable pole is Mathieu accessory parameter. Well, what you have to write? So if you write the Q function in the neighborhood of a movable pole, so as far as I remember, it's a second order pole, so you will have something like this, where the coefficients depend only on T naught, T minus T naught, and then you will have a finite part plus something else. So this finite part is essentially Mathieu accessory parameter. Well, yes. So okay. So we can come back to this question later because I will show the Lux pair and so on. But the kind of relation that I want to discuss, at least naively, looks different from this. Okay. So it was more or less the plan of the talk. So now I will try to go more into the details. And I will start with the Mathieu equation. So as I told you, this is a Schrödinger equation with periodic potential. Therefore, well, the corresponding Hamiltonian commutes with translations by pi. And this means that we can look for solutions of this equation in the Floquet form. And nu here, this will be an important parameter. This is precisely the eigenvalue of the translation operator. So if you plug this ansatz into the equation, then you get this difference equation for the coefficients. And this is homogeneous. Therefore, a non-trivial solution exists only if the determinant of the corresponding matrix vanishes. And this is precisely this determinant. Here I have to introduce some denominators in order to make this determinant well defined. And this determinant satisfies a surprising relation, which allows you to write a condition on the spectrum, so on the energy as a function of nu and the coupling constant R in this form. So this implicitly determines E as a function of nu and R, and you can try to solve this equation by a perturbative series for small r. Not very difficult. So this function E of R and nu is even implemented in Mathematica as Mathieu characteristic A. But surprisingly, at least for me, Mathematica doesn't know how to expand this function into series. But, well, anyway. So an easier way to get this perturbative series for Mathieu accessory parameter is the following. So the trick is very similar to how you convert a linear second-order differential equation into a Riccati first-order nonlinear differential equation. So basically, you do this rescaling of the coefficients. You introduce these ratios. Then instead of second-order difference equation, you get this, which means that you have this equation determining un minus 1 in terms of un, and this means that u0, which is the ratio of a1 over a0, has this continued fraction representation. On the other hand, you can repeat the same trick with n less than 0, and use finally an equation for the coefficients a plus minus 1 and a naught, and this leads you, this gives you this equation. So now if you want to know this expansion up to some fixed order, then just truncate, plug it into this formula, expand in Mathematica, and this will easily give you all the coefficients that you want. Okay, now let us go to Painlevé equations. So Painlevé equations arise in the solution of the inverse monodromy problems for linear ODEs with rational coefficients. And so to explain this, I will start with my favorite example, Fuchsian system, 3 regular singular points at 0, 1, and infinity. So the fundamental matrix solution of this has monodromies around these points. And we have a map then which goes from the space of Fuchsian systems into the space of monodromy data. And one can ask then 2 questions about this. So the first question is, so I will refer to it as problem A. So find the Fuchsian system which has given monodromy. This can be easily solved because actually the, at least in the rank 2 case, because the in the 3-point case, the residue matrices as well as monodromies are completely determined up to conjugation by the eigenvalues, which I denote here by thetas. One can ask another question, so this problem B. So this is not to construct a Fuchsian system with a given monodromy, but to solve it. And this is also doable, but not so easily. The solution will involve Gauss hypergeometric functions. Okay, so of course, if you have a solution of the problem B, you can always extract from it the solution of problem A. But this problem is actually much easier than this one. And somehow we will try to address directly the problem A. Okay, and where are Painlevé functions here? So if we add one more regular singular point to the system, so let's call it T, then the dimension of the space of systems and the dimension of the space of monodromy data will be equal to 2. And this gives a possibility to do isomonodromic deformation. So if you, if for every value of T, you are able to find the system of this form, then we know that the residue matrices A0, AT, A1, they satisfy these classical Schlesinger equations, which are equivalent to Painlevé 6. But the message here is that one, in order to solve Painlevé 6, one shouldn't try to solve this equation. Instead of this, one has to try to construct the linear equation with a given monodromy. Then, if you manage to do this, then automatically you have the solution of your differential equation, the general solution. Now, the Painlevé 3 D8 that I mentioned in the beginning is obtained in a similar way by confluence. So here I have a kind of geometric picture. So this surface corresponds to 4 simple poles. And then you try to degenerate. So for example, Painlevé 5 arises when you do isomonodromic deformations for systems with 2 simple poles and 1 double pole and so on. And this equation is the equation of isomonodromic deformation for systems having only 2 irregular singularities, 2 second-order poles, such that the leading contribution at the corresponding singular points is non-diagonalizable. So this is the general form of such a system. So this system is parameterized, as you see, by some letters P, Q, T, and so on. It has some monodromy data that I don't really want to explain. But the point here is that if you manage to construct such a system for every value of T, which gives prescribed monodromy data, then automatically your function Q will solve Painlevé 3D8. So it is related to this radial Saint-Gordon equation by this simple formula. Right. So now how can we address this problem A? So this was basically the subject of my talk at the first workshop, where I treated it for Painlevé 6. So I will just try to go quickly along the different steps. So the first one has to convert the linear system into a Riemann-Hilbert problem, which initially has constant jumps. Then the game is to transform this Riemann-Hilbert problem into another one, which is a Riemann-Hilbert problem on a single circle. And the jump matrix in this new Riemann-Hilbert problem is constructed out of solutions of two auxiliary Riemann-Hilbert problems, which correspond to linear systems with one second order pole and one regular singularity. So this auxiliary Riemann-Hilbert problem one can actually solve in terms of Bessel functions. Now, once you have this, you can use Widdom's variational formula to identify the so-called tau function, isomandromic tau function of Painlevé 3, with a certain Fredholm determinant, whose matrix integral kernel is completely explicit, and it is given in terms of this auxiliary solutions phi plus minus, in terms of Bessel functions. So I have written here a graphical representation of the corresponding identity. So if you have a system with two irregular singular points, then the tau function is the product of these two auxiliary simpler tau functions, where the irregular singularity is replaced by a Fuchsian one. And then one has some determinant, which again involves only this Bessel type functions. And finally, when you have this Fredholm determinant, you can expand it into a sum of principal minors in the basis of Fourier modes, because the corresponding kernels, they act on functions defined on these red circles. And in this way, one gets an explicit series representation of the tau function, which is related to this q and phi by the simple formula. So basically, the logarithmic derivatives of the tau function allow you to construct the solution of problem A. Okay, so this is the solution. So the first part of the solution. So the tau function is expressed as a determinant. So here you have some integrable kernels, A and D. So this matrix J is constructed in terms of Bessel functions. So the explicit formulas here are not so important. I just wanted to show you that the result is completely explicit, and you have two integration constants which are sitting here. It's this variable sigma and the variable eta. So these are arbitrary complex numbers. Now the series representation that you obtain by expanding this determinant into a sum of principal minors has this structure. So it is rather surprising. At least I don't know how to see this Fourier transform structure by just looking at the Fredholm determinant, but this is somehow the result that you get. So the tau function is given by a Fourier transform of some other function which involves only one of the monodromy parameters, and the other parameter appears here as a Fourier conjugate variable. And the function B, well, it has a completely explicit form. It's a sum over Young diagrams with some explicit rational coefficients. So A and L here are the arm and leg lengths of the box in the corresponding Young diagram. And of course, one can compute a few terms in the expansion of this function explicitly. So you have something like that. You can continue and compute many more if you want. And the question that we ask, basically, is there any relation between this function b, which appears in the expansion of Painlevé 3D8 tau function, and mature accessory parameter e of R and nu? So to answer this question, I will introduce a new actor in the story, which is Virasoro conformal blocks. So here we start with the Virasoro commutation relations. We consider a vacuum vector which is annihilated by all generators with positive indices. So this will act like annihilation operators. And so this vector is an eigenvector of the generator L0. From the vacuum vector, you generate the so-called descendant states. So you have a lot of creation operators, L-1, L-2, and so on. So these descendant states, they will be basically labeled by, again, Young diagrams. Okay, so for example, to this state, you can associate a Young diagram which is like this. So you have 4 boxes, then you have 2, then you have 2 more, and then you have 1. These descendant states, they diagonalize the operator L0, and the total number of boxes in the corresponding Young diagram is called the level of descendant. One can similarly introduce the dual vacuum, which will be annihilated by all creation operators, and then to define a canonical pairing between the corresponding Fermat modules. So, for example, here I just show you how to compute a scalar product of this vector in here and this vector which lives in here. So basically, you just use systematically the commutation relations, and ultimately you can reduce everything to the norm of the vacuum vector. Okay. Then, almost the final step is the introduction of the so-called Whittaker vector. So the Whittaker vector is a vector in our Fermat module V delta, which is the joint eigenstate of all annihilation operators, but a very simple one. So one has only one non-trivial eigenvalue for L1, and all other annihilation operators, they act by 0. Okay, so you should think of this Whittaker vector as a kind of coherent state in quantum mechanics, but of a very simple kind. Now one can write a decomposition of this Whittaker state in the basis of descendants, and using commutation relations of the Virasoro algebra, in principle, one can compute the coefficients of this decomposition explicitly. So if one is persistent enough, you can just go up to any level in descendants and compute. And now the definition, the main definition here, is the one of conformal block. So the conformal block is just the norm of the corresponding Whittaker state. Okay. So using this decomposition that I had here, for example, so once again you just use systematically the Virasoro commutation relations, and you end up with a certain expansion of this function f of t. Now, an important fact is that there exists an explicit combinatorial series representation for this function in the form of a sum over pairs of Young diagrams. And this series representation may be used to identify this conformal block with the function b, which appears in the decomposition of the general solution of Painlevé 3. So Painlevé 3 function is given by this conformal block for central charge equal to 1 and for this delta equal to mu squared. And if you really want to put your hands on this concept of conformal block, you can just try to compute the corresponding expression in the case of SL2 algebra instead of Virasoro. Then you don't have central charge, you have only a finite number of generators, then the computations are really, really easy, and you can just check by hands in maybe half an hour that the corresponding conformal block is nothing but the Bessel function in the case of SL2. Now, where is the Mathieu accessory parameter? Well, it turns out that if you consider the so-called quasi-classical limit, where you send the central charge and the conformal weight and the argument of conformal block to infinity, but in a correlated way, then the corresponding function f exponentiates. So one has this WKB type asymptotics. Again, conjecturally, one can just check it order by order, but up to my knowledge, this was never proved. And well, computing several first terms in the expansion of this function, one obtains this expansion. And well, there are little chances that you remember what was the expansion of Mathieu accessory parameter, but basically we have exactly the same expansion, except that these denominators, like 2, 32, 64, and so on, so here they become they become 8, 256, and so on. And nevertheless, it is easy to guess what is the relation between the two functions. So the Mathieu accessory parameter is basically the derivative of the classical conformal block. Good. Now okay. So the last point, this is almost the last slide, is the blow-up equation. So blow-up equations are some bilinear identities which relate conformal blocks with different central charges. So the central charges here are parameterized by a parameter b, and by choosing this b appropriately, so basically by sending, so you see here b plus and b minus, they are both functions of one and the same parameter b. So when you send this parameter to 0, then basically this conformal block will be characterized by central charge infinity, and this by central charge 1. And if you work out really the details, what is going on, assuming the exponentiation conjecture, then what you get is an explicit identity which involves, so on the right-hand side, you have here C equal to 1 conformal blocks which appear in the decomposition of the Painlevé 3 tau function. And here you have essentially Mathieu accessory parameter. So an explicit identity. So one last remark is that so the right-hand side here looks very much like the Painlevé 3D8 tau function. So you see it has this Fourier structure involving C equal to 1 conformal blocks. And the second monodromy parameter here is basically the derivative of, again, classical conformal block, but not with respect to R, but with instead of this, with respect to nu, with respect to monodromy. Okay, so I list here some open questions, and thank you very much for your attention.
Could the next speaker set up? Any quick questions while that's happening? Okay, looks like we can defer them to coffee break. So thank Oleg again.